In this video, I'm going to talk about my research into building a low-cost, terabyte-scale data storage solution. To be more specific, I wanted a solution that would let me take several physical hard drives and combine them together into one large-capacity file system. The setup that I ended up using consists of a Raspberry Pi 4 running Ubuntu 20 with the ZFS file system, and a Saiba 4-bay 3.5-inch hard drive enclosure. The Raspberry Pi connects to the hard drive enclosure over a simple USB connection. Initially, I had considered an even more bare-bones approach with a simple Raspberry Pi directly connected to multiple hard drives over USB to SATA cables. I eventually decided not to use this approach, and I'll discuss why later in the video. I'll also talk a bit about why I chose to use the ZFS file system instead of the alternatives. In terms of considerations for selecting the hardware, read and write performance was not a priority for me. Instead, I was looking for something that could ensure the integrity of the data and automatically recover in the event of a hard drive failure. Another consideration was I planned to keep this turned off probably 99% of the time. When most people build a setup like this, they're looking to use it as a network-attached storage. In my case, I don't plan to use this over the network very much, so fast networking hardware is not a priority for me. Another consideration was I wanted to explore the absolute bare minimum, lowest possible cost multi-hard drive setup, even if that meant that the hardware had some limitations that made it not very practical. For example, people say that you should use ECC memory when using the ZFS file system. In this case, I just have a Raspberry Pi with 4 GB of non-ECC memory. Another consideration was to make sure that the hard drive enclosure was a non-RAID enclosure. Certain file systems like ZFS work best when they have direct access to the underlying hardware. Running ZFS on top of hardware RAID is technically possible, but generally not considered optimal. Some hard drive enclosures can come with their own built-in hardware RAID controllers. Or they can come with a variety of built-in software for managing the file system. In my case, I didn't want any of that. I just wanted a USB connection from the Raspberry Pi to the hard drives itself. And the primary function of the enclosure was just to keep the hard drives safe and to power them. Now, you're probably wondering why I couldn't just take a Raspberry Pi and use the 4 USB connections to plug it into 4 hard drives. I can tell you from experience that you can run a single 2.5-inch hard drive using one of these cables on a Raspberry Pi, but you'll run into problems if you try to run more than one hard drive, or if you want to power a 3.5-inch form factor drive. The problem with trying to do this on a Raspberry Pi is that you're most likely going to run into issues with drawing too much current. The maximum current draw that a Raspberry Pi can support will depend on the version of the Raspberry Pi, as well as the quality of any cables that are hooked up to it. This means that if you fill up all the USB ports on a Raspberry Pi with devices that require power, you can easily exceed the current limits of the Raspberry Pi. It's not just the current limits of the Raspberry Pi that you'll need to be considerate of either. These USB to SATA cables also have a few internal limitations that I'll illustrate by looking at them internally. So I currently have the USB to SATA adapter plugged into the USB 3 port of the Raspberry Pi. And here I've printed out what I believe to be a pinout of the SATA 3 pins. So up here are the data pins that would correspond to the few pins up in this region. The orange 3 volt there, that would be this one up here, and the 12 volt yellow, that would be way down here. So if I can, I'm going to try and very carefully probe onto this to actually measure the voltages. So first I'll try to probe onto pin 5, which is supposed to be the ground. And according to the spec, that's supposed to be 3.3 volts, but it looks like it's closer to 0. Now, also according to the spec, these are supposed to be 12 volts with respect to ground. And I don't see that. And this pin in here looks to be 5 volts, which matches the spec. So it looks like the 3.3 volt and the 12 volt don't match the spec and are just set to nothing. So I think there's probably a very good reason why these USB adapter cables are not setting the 12 volt pin. And that's because according to the USB specification, the maximum current that USB 2.0 supports is 500 milliamps at 5 volts, and for USB 3, it's 900 milliamps at 5 volts. According to the label on one of my 2.5-inch drives, it requires 1 amp of current to operate. So it's surprising that it works with this cable at all, considering the fact that the hard drive supposedly requires more current than the USB spec allows. Looking at the label on one of my 3.5-inch hard drives,
It says that it requires 550 milliamps at 5 volts and 370 milliamps at 12 volts. If you were to boost the 5 volt USB power to 12 volts at 100% efficiency, you'd need an additional 888 milliamps at 5 volts. This would mean that the source powering the USB cable would need to supply almost 1.5 amps at 5 volts. Since this is likely more power than the USB source could supply, the manufacturers of this cable probably didn't even bother to supply power to the 12 volt pin at all. Having said all that, I generally consider these hard drive power specifications to be woefully inadequate, and I take them with a grain of salt. There is no mention of what operating conditions these power specifications are intended to represent. It's also worth noting that each of the drives that I have lists fairly different values for the power requirement. This Western Digital 3.5 inch lists slightly different numbers: 600 milliamps for the 5 volt and 450 milliamps for the 12 volt. And the Toshiba drive lists 700 milliamps for the 5 volt and 850 milliamps for the 12 volt. With all of this in mind, it's worth noting that if you search on eBay, you will find some USB to SATA cables that claim to work with 3.5 inch hard drives. However, for each of these products, it looks like they all require an additional 12 volt power supply to function properly with 3.5 inch format drives. This, of course, would add a lot of additional cost and clutter for every drive in your setup. This is not surprising given what we've learned about the 12 volt pin not even being powered on the USB to SATA adapter cable itself.
Okay, now I will do some demos to show what happens with this USB to SATA cable. I've got it plugged into the Raspberry Pi here, and I'll try it out with a 2.5 inch SATA hard drive and a 3.5 inch SATA hard drive. Okay, so it's in the 2.5 inch, and I can hear it spinning up. There is the device. So now I will unplug that, and I can see it disappeared. So now I'll plug it into the 3.5 inch. So there's no spin up, and I do not see it showing up. And by the way, it's plugged into the USB 3 port right now. Now let's try this in the USB 2 port. So I can hear it spinning up, and there it is, it's detected. Let's unplug that. Okay, it's removed. And in the 3.5 inch, so it does not show up in the 3.5 inch. So this cable works with the 2.5 inch hard drive in the USB 2 and USB 3. Okay, now I'll try the second cable. So this one works with the 2.5 inch drive, and it's not picking up the 3.5 inch drive, and I don't hear it spinning up either. So I now have it in the USB 2 port, so I hear it spinning up, but it looks like it's not detected. And let's try it in the 3.5 inch. And not surprisingly, it's not detected.
You could probably get it to work with one of those adapter cables that comes with the additional external 12 volt power adapter, but I don't have one of those, so I can't test it.
So there's really two lessons here. I was able to get the 2.5 inch drive to work in some configurations with the cable. The 3.5 inch drive didn't work with either of the cable, with either USB 2 or USB 3. And the second lesson is that not all cables are equal. For the 2.5 inch drive, this cable was able to work in the USB 2 and the USB 3 port on the Raspberry Pi, but this cable only worked in the USB 3 port. I find that kind of ironic because I would expect the cable branded as the USB 3 would be, the more advanced one, and I thought that USB 3 was backward compatible. But it seems like this only works in the USB 3 port and not in the USB 2 port. And ironically, it's the USB 2 cable that works in both the 2 and the 3. And while I'm at it, I might as well show what these cables look like inside. It's also worth noting that the current draw of a device varies continuously as you use it. For any device that contains a motor, the maximum current draw is almost certainly going to be when the device starts up. If you're running multiple hard drives at once, they may run continuously for a long time without any problems. However, if you go through a short period of time where all of the disks start accessing random sectors at once, this could cause the current draw to spike and momentarily exceed the maximum current rating of your Raspberry Pi. In a best case scenario, the device would simply power off, or you might get hard to detect data corruption or system instability. A slightly better alternative is to use one of these powered USB hubs. With one of these, you can use a single connection to the Raspberry Pi and still communicate with all the devices that are plugged into the USB hub. With one of these, you have a much greater hope of being able to successfully run many high-power USB devices with your Raspberry Pi. Having said that, the reason I ended up not using this approach was because I checked some of the reviews for these. And most of the models that I investigated either had problems with the maximum current support. Some people described problems like if you plugged in the first 4 ports, the last few would not work properly. And another consideration is to think about how clean the power supply is. When your power gets stepped down from 120 volts AC to 5 volts DC, there are all kinds of components along the way that are supposed to filter out any fluctuations or noise in the signal. Unfortunately, many of these USB power banks seem to produce very noisy power. This is not a problem for something like a USB keyboard or a computer mouse, but this can be a real problem with a highly sensitive device like a hard drive. From some of what I've read, people have suggested that you can run hard drives on unclean power, but this can significantly reduce the lifetime of the drive. Since I'm using this as a backup solution, that kind of defeats the purpose, so. In theory, it should work, and I may do some experiments with this in the future. And for a USB hub like this, I paid $36. For the Raspberry Pi 4, I wanted one anyway for some other projects, so I decided to just buy a kit that comes with a fancy case, a fan, and the USB power cable, and also the flash drive. This was $175, which kind of violates the cheapest bare bones rule, but I have a suspicion that you might be able to get this same setup working on the older Raspberry Pi 3, although I haven't tried that yet. The Saiba 4-bay hard drive enclosure was $156, which is a pretty good price compared to some of the other ones online. I actually put 4 different hard drives in this enclosure, and those are a Toshiba N300 4TB NAS internal hard drive at 7200 RPM. That was $129. 2 identical Seagate Ironwolf 4TB NAS hard drives at 5900 RPM. A Western Digital Red Plus 4TB NAS hard drive at 5400 RPM. Now I'll talk a little bit about the file system and software considerations. Since I don't plan to use this as a network-attached storage, I actually don't want there to be any kind of special software running on the hub. And if you're like me, you're probably wondering, can the Raspberry Pi recognize this storage hub right out of the box? And the answer to that question is yes. When you plug in the USB here, if you run fdisk-l on the Raspberry Pi, you'll see all the drives show up from the hub. In this case, it works just like any other USB hard drive, only you have 1 cable instead of 4. As far as I know, there's also no kind of management software or web-based interfaces on the hub itself. And in my case, that's exactly what I wanted. It's one less thing to have configured, one less thing to be hacked into, and one less thing to stop working randomly in the future. For the choice of operating system, I went with Ubuntu 20, which conveniently runs on a Raspberry Pi now. This is great because you can get the ZFS file system working in just a couple of commands on Ubuntu now. In terms of the file system, it would have been possible to format all the drives as something like ext4, but to the best of my knowledge, there is no easy way to get all of that storage capacity aggregated together in one logical file system with ext4. This led me to search into alternative file systems. The 2 major ones that people kept bringing up were ZFS and BTRFS, or BTRFS. I read a lot of forum posts and watched a few videos by the people who actually work on ZFS or BTRFS to try and figure out which one would be a better file system for me. A recurring theme was that people discussed these 2 file systems as though they had a fairly compatible feature set. On the surface, that seems to be true, but what I found is that most people seem to talk about BTRFS when they're discussing things like file system efficiency, features like snapshotting, high performance when they're passing through the file system in a virtual machine. But when it came to the data integrity side of things, it really seems like BTRFS is lacking. In fact, there's a quote floating around where someone was discussing the support for one of the RAID modes in BTRFS, and they described it as broken beyond belief. In contrast, most of the conversations about ZFS seem to obsess about things like data integrity and recovery from failure. There are a few people who pointed out things like lower efficiency on ZFS and less advanced snapshotting features on ZFS compared to BTRFS. So from all the research, it seems like ZFS is better if you care about data integrity, but BTRFS is better if you care about day-to-day use cases and things like efficiency or snapshotting. Since this was a backup solution, the choice for me was clear, and I went with ZFS. Another thing worth considering is the fact that the ZFS file system is a really old idea. And you should make a distinction between the idea of the ZFS file system, in terms of things like specifications, and actual implementations. In the open source world, you may find different implementations of ZFS that have varying degrees of completeness and correctness. So in terms of my first impressions with ZFS, I was able to get this working, and I've been using this for a couple of months now with no problems. I did, however, encounter one strange situation that could have led to data loss. In terms of how you provision your system with ZFS, you can either prioritize high integrity or high use of the disk space. In my case, I decided to provision this as a RAID Z2 setup. And if I understand correctly, that'll mean that I can lose up to 2 of the hard drives and not lose any of the data. The disadvantage of that is that even though I have 16 terabytes of physical storage here, I only have 7 that are usable. The rest is all used up with redundancy. I don't know nearly enough about ZFS yet to give a tutorial on it, but I do plan to use it more in the future. There are a lot of things that I don't understand about ZFS yet, but if I had to use one word to describe it, I would say it's a very sticky file system. What I mean by that is it seems to be difficult to get it to make changes for you. I think this is mainly a heuristic to try and preserve the integrity of the data, but I also found that if you end up in an error state with ZFS, it's really difficult to figure out what's going on and how to recover it back into a normal state. And if you try to do research online about how to repair or recover a broken ZFS system, most people will just say, just copy out the files that you can and then rebuild it from scratch. One more consideration for the hard drives was I decided to select only hard drives that were considered NAS drives. You'll find a few reports out there where people say they had problems running ZFS on SMR drives. I think the problem there is that since SMR drives are so slow, if one of them actually fails and you need to rebuild the entire RAID array, and the rebuild process takes on the order of a week or 2, the probability that a second hard drive will fail simply by chance during that time is pretty high. Another thing that I should mention about this drive bay is that it really makes a big difference whether you plug it into USB 2 or USB 3. When I first put the drives in, I decided to run bad blocks on all of them just to test them for errors. Initially I did this over USB 2, and that process took about 8 days to finish all 4 of the drives. I then repeated that test, and it took 2 days over USB 3. Those numbers are pretty much in line with the theoretical maximum transfer speed of the single USB cable. Something else that people suggest is a best practice with ZFS is to make sure that all of your drives are of the same make and model. In my case, I did the complete opposite of that, and nothing bad happened. All 4 of my drives are 4 terabyte hard drives, but they're from 3 different manufacturers, and there's at least 3 different hard drive speeds, 7200, 5900, and 5400. Another thing is that I didn't use ECC memory and nothing bad happened. Okay, now I'll do some review of the notes that I took when I first set up this ZFS installation. So I won't do a full tutorial of this, but I'll just review some of the commands that I used. This was the command that I used to install ZFS. When I set up the ZFS pool, I decided to list the disks by their ID. I figured that it would be more reliable to set up the disks according to their disk ID as opposed to SDC, SDA, and so forth. The ordering of SDA, SDB, etc., that stuff can change every time you reboot, so it's not reliable. However, after I set up the pool, it seemed to default to those anyway, so I don't know if that'll cause problems in the future. From what I understand, I think ZFS is intelligent enough to not depend on those labels. And here's what it looked like when I ran df before setting up the pool. Here's the command that I used to set up the pool with RAID Z2. Then, after running df, the ZFS pool shows up here. And running zpool status, I can see some more information about the pool here. Another useful command is zpool list. And it seems I also had to change the permissions on this folder so I could write to it. Here I was just doing an initial test and writing a test file to the pool. Here is a test I did where I unplugged the USB cable just to see what would happen. And here in the output of zpool status, you can see it's identifying a read issue. And in my notes here, I had wrote that I ran the ls command in that directory, and apparently it hung and I was not able to kill it. After plugging in the storage bag in and running zpool status, I still got the error message. And I had to run zpool clear, and that got rid of the error. Now, this is one of the error messages that I had a lot of trouble with in ZFS. From what I understand, this will normally reference a file if it detects that a file is corrupted. But if you get this 0x0, that means that something in the metadata of the file system is corrupted. Now, one of the things that got me into trouble with ZFS was I decided to really be aggressive and test it. So I was in the process of copying a bunch of my old files onto the ZFS pool, and I decided to, while the storage bay was plugged in and running, I just pulled out one of the drives, and at that instant, the transfer rate dropped to 0, so it stopped moving. It basically just hung. Once I pushed the drive back in, it would start transferring again, and at that point, I was actually kind of impressed because it looked like it was just going to continue the transfer. It transferred all the rest of the files, and I was able to see, pretty much everything that I thought was going to copy. It looked like it copied over correctly. The next day when I woke up and checked it, though, I saw this 93.1 thousand checksum errors in the pool, and I figured that couldn't be good. So I tried a bunch of stuff to get this thing into a good state. And of course, here's that pesky error message that I wasn't able to get rid of before. If I recall correctly, it originally listed a file, and I decided, okay, I'll just delete that one corrupted file from the file system. And by the way, it happened to be the file that I was copying at the instant that I unplugged the drive. I'm a bit disappointed in that because this is supposed to be RAID Z2, which, if I understand correctly, that should behave correctly as long as I don't experience more than 2 drive failures. So in this case, I only unplugged one drive and put it back in, but somehow that file was still able to become corrupted. I don't know if this is something I can blame on ZFS, or it might be an issue with the actual hardware setup. So I know that in order for ZFS to work properly, it has to be able to trust the hardware. So if ZFS is doing writes, but it thinks the writes are committed to disk, but they're actually not, then that's one source of problem. It's possible that there's some kind of controller in the storage bay itself that's maybe interfering with this process. I'm really not sure. Anyway, I got stuck in this state where I would say it was resilvering, and the number of checksum errors just kept going up. And no matter what I did, I was never able to clear this my first ZFS pool 0x28f error. And the only suggestions that I could find online were people saying that you should just copy off the files that are not corrupted and then restore from backup for the one that is. So in my case, this was already a backup, so I just did zpool destroy to get rid of that ZFS pool. And then I recreated the pool again, and I made sure to not unplug any of the drives. Now, the process of recreating the pool was also a huge ordeal, because every time I tried to do that, I would get this error message that's saying that the pool is imported on a different host, which it obviously is not. I figured that was probably because there was some information in the boot sector of the drives, and that was making it pick up the old pool. So I figured if I just wrote some random bytes to, say, the first 1 megabyte of those disks, and maybe that would resolve the issue and they'd be considered unformatted. I tried a bunch of different stuff like rebooting the Raspberry Pi, but in the end, what fixed it for me was rebooting the storage bay. So I don't know what's up with that, but that implies that the storage bay itself was caching some kind of hard drive information, and that was interfering with the recreation of the pool. Okay, let's SSH into the Raspberry Pi and take a look at the pool. So I just rebooted the Pi, and if I do df, I don't see the pool here. So what I have to do is sudo zpool import -a. And I can hear the drives spinning up. Now if I do df, there we go, my second ZFS pool. So here I can see the pool looks like it's fine. I did a scrub recently, which took 16 hours. And here's another basic ZFS command that lists some information about the pools. So one of the primary features of ZFS is it stores checksums along with all the data, and checksums are around the metadata. So if you end up getting a drive that gives you back some bad data, you should hopefully see some errors in here. Now, just because you see zeros here doesn't necessarily mean all your drives are healthy. It could be that there's some corrupted data on there, but you just haven't tried to do a read of it recently. And that's what this idea of a scrub is. It just scrubs through all the data and reads it, verifies the checksums, and makes sure that none of the data is rotting away and inaccessible. From what I understand, it's actually quite common for a hard drive to start giving you bad reads for a while, maybe spuriously, but overall the drive can actually continue to work. And this is where ZFS really shines, because you can have, theoretically, a bunch of kind of half-failing hard drives, and you can still get some useful work out of it. And as long as there is at least one good copy of the data, then theoretically your system should work fine. Something else that I wondered about before I used ZFS was the idea of mounting. With something like ext4, you have to run a mount command before you can actually access what's on the drive. But with ZFS, you can see here that these drives are actually not mounted. At least not in the way that you would with an ext-based file system. So I guess with ZFS, the drives are mounted on a pool-based level, as you can see here in the output of DF. Okay, I think that's everything I wanted to say. Hopefully I've given you a good idea whether or not you want to try out running ZFS yourself on a Raspberry Pi.